Okay, so thank you for your introduction. I just would like to mention that this activity was carried out at MEMS laboratory, University of California, Davis, and Berkeley Sensor Actuator Center under Professor Horsley supervision. So my presentation will start with an overview of the implementation of the device and then its electromechanical characterization. Electrometers are instruments to measure precise amount of charge, and they can find application in many different fields like radiation detection, scientific instrumentation, chemical, physical, biological experiment. And as an example, optical particle counters in instruments to measure aerosol can be replaced with MEMS electrometer, being less cumbersome. So in this scenario, the interest to develop electrometers using MEMS technology is justified by the reason to reduction of cost, weight, power consumption. So the prototype we are going to show is based on a vibrating capacitor of a MEMS resonator, and when an external amount of charge is deposited on the sense capacitor, it is converted into an output voltage, which is an alternated signal because of the modulation of the capacitor. The sensor we have implemented is based as a main frame, which is supported by which is anchored by 4 springs, and there are 2 sets of lateral conductors and for motion sensing. Finally, there is a parallel plate capacitor, which allows for charge sensing at twice the resonance frequency because of the specific geometry of the capacitor. So I will show you later that we are using a narrow band battery. The mechanical sensitivity of the device can be improved with the maximization of the MEMS rest capacitance, as well as a maximization of the linear displacement and the reduction of parasitic components loading the input node. So during the design of the system, so the system design flow, the next step was finite element simulations in order to verify that higher order vibrating modes do not overlap with the sensing signal, which is at twice the resonance frequency. The device was implemented using ST Microelectronics Thelma process, the thickness of which is around 15 microns. And here you can see the external frame with the lateral set of thumb fingers, and this is a close-up of the parallel plate capacitor for charge measurement. The next step for device characterization was an electromechanical characterization, which consisted of a quasi-static analysis to measure the capacitance variation and to estimate the pull-in voltage and elastic stiffness of the device. But more important is the frequency response of these devices in order to measure the actual resonance frequency, because they are driven at their resonance frequency. So a first prototype of a system for charge measurement was implemented based on these devices, and we achieved a resolution of about 1,000 electrons per square root hertz. Possible improvements for these systems can be done in the MEMS to electronic coupling and in the reset and calibration mechanism. And I'm going to show you this improvement. So let me give you some details about the design of driving and readout electronics and the reset mechanism we have implemented in our new setup. So as a guidelines for readout analog front-end design, they are set by the need to measure low amounts of charge, which flows on the vibrating capacitors, and they turn out into a small AC voltage signal. So reduction of leakage, low input referred noise, and minimization of parasitic capacitances play an important role. As far as MEMS oscillation, I'm going to show some improvements of a scheme for open loop driving. But as an ultimate goal for this project, an implementation of a closed loop self-oscillating circuit would be of great interest. So the driving circuit is based on 2 different unity gain amplifiers, which allows to they split the external stimulus into a phase signal and into an antiphase signal, which are used for the push-pull driving. This kind of driving is common for many sensors, many actuators, because the force is linearly controlled by the applied voltage. The choice of OPA 445 operation amplifier is mainly due to its capability of stand high voltage with a low offset drift and fast slew rate. The choice of resistors value is mainly due to minimize the gain mismatch between the two branches, and we have measured a flat bandwidth response up to a few tens of kilohertz, which is enough for our devices driving. The sensing circuit is based on a non-inverting closed loop amplifier with a very high input impedance. The choice of AD8067 operation amplifier by analog devices is mainly due because of its good trade-off among input noise, leakage current, and input parasitic capacitances. This operational amplifier has a common mode capacitance of about 1.5 picofarad, which is also due to the tiny package of the operational amplifier itself. We have measured the leakage current a little lower than 1 picoampere, and the design of feedback resistors for the gain of this closed loop amplifier is done in order to make their noise negligible with respect to the unavoidable operational amplifier noise. We have measured a 10 nanovolt per square root hertz noise, which is quite in good agreement with the theoretical prediction. And finally, with respect to fast implementation of our setup, we have replaced the mechanical reset with an electronic reset, which is done using a FET by NXP semiconductor. And this transistor is designed for low loss and isolation application. So finally, I'm going to give you some details about the accurate assembling of the setup and the system we have used to filter signal. So the design amplifier to sense the voltage on the MEMS is connected to a lock-in external amplifier, and the output data are digitalized by a data acquisition card. The driving circuitry for push-pull driving is controlled by an external waveform generator, which also provides the reference signal for the synchronous demodulation and filtering. This is the implemented setup, and there is a motherboard which hosts the driving section of the setup, and there is a daughter board where the MEMS is closed and to the readout electronics. This solution is implemented to minimize parasitic capacitances, and wire bondings are very close to readout electronics. Also, the connector for charge measurement is very tiny and low loss. The reset transistor is on the bottom of this daughter board. So you can now appreciate the difference between the first implementation, where the MEMS was alone on the middle board. Because of the leakage integrating on the input capacitance, this system requires to be resetted periodically. And I would like to mention an issue about the reset in this case. The transistor requires about minus 3.5 volts to be switched on. And this signal gives a charge injection on top of MEMS capacitors, which is of course unwanted, because otherwise the initial measurement can be affected. So in order to avoid this charge injection, the amplitude of the signal controlling the gate of the transistor can be reduced, or otherwise the fall time can be slowed down. A reduction in the amplitude cannot be done because otherwise the MOSFET doesn't work correctly. So this is the reason why we have slowed down the edge of the driving signal of the gate of the transistor. Calibration of the system is performed applying an external step through a calibration capacitance, and we have measured a sensitivity of about 50 microvolts per femtocoulomb, which results in a resolution of about 1.3 electrons per square root hertz. So summing up, we have implemented an electrometer using an industrial standard MEMS technology. And also we have redesigned our setup, driving and readout electronics, with a specific purpose to reduce parasitic capacitances, leakage current, and noise. And also an important role was played by the accurate system assembling, as I shown you before. Among ongoing and future activities, we have designed a second generation of devices, changing the thickness of the process from 15 microns to 22 microns, and this will result in an improvement of the intrinsic mechanical sensitivity because of a higher MEMS rest capacitance. As an ultimate goal for this project, design of bullets-eye electronics would be of great interest, because in that case we can reduce parasitic capacitances in the coupling of the two chips, and possibly this MEMS system will be integrated in NR quality measurement unit, like replacing the optical particle counters in aerosol measurement suites. Thank you. During calibration. And so, what do you mean with? Well, okay, I got it. So we have implemented many different small boards in order to characterize different devices. So we have calibrated each single board, because the assembling process can add different parasitic capacitances. So for each small board, we have performed a calibration, but the calibration is done only once at the beginning of the when the system is switched on, and then many measurements can be done using the reset system to avoid the saturation of the amplifier.